right? So lower order harmonics and higher order harmonics. So lower order harmonics in the sense, in all the cases, lower order and higher order will not have any even order harmonics. Only odd harmonic odd orders will be present. That is 3, 5, 7, 9. All will be present. And in three phase, the multiples of three, that is a triplet harmonics, will also be absent, right? So only the even numbered harmonics will be absent, and in three phase the triplet harmonics, that is the multiples of three third order harmonics will be absent. So the predominant harmonics are the odd numbered, and non-triplet harmonics will be dominant in the output voltage. That is 5, 7, 11, 13, likewise. So these are all the harmonics that will be dominant in case of three phase. And in single phase, all the three third three and multiples of three will be present. So the lower order harmonics will be depending upon the order. So up to 11th order we can have as the lower order, and beyond the 11 we can have the higher order harmonics. 11 beyond 11 means 13, 15, and up to n we will be having the higher order harmonics. So already I have told the higher order harmonics can be easily removed using the filter. So already I have shown that expression. That is a the filter will be having some L and C components. The size of the L and C components will be less for the higher frequencies, and the cost is also low for that filters. And the lower order harmonics is a very difficult task to remove that, and we have to specially design for that filters. And the filter size will also be large. If the frequency is less, the frequency will decide the size of the filter, and it will also be high, and it leads to higher costs. So now we are going to see what are the reduction techniques. So we have to reduce the lower order harmonics in the output voltage, and higher order harmonics we can easily suppress. So for that, for reducing the lower order harmonics, first one we can have PWM, that is pulse width modulation technique. Next, by means of transformer connections and by means of stepped wave inverters, we can reduce the harmonic contents. So now these are all the basic methods. Now there are many advanced methods for reducing the harmonic contents. That is selective harmonic elimination. That is selective harmonic elimination in the sense the harmonic which has to be eliminated. We can choose the number. That is, we can first thing we have to reduce the fifth order, seventh order, and ninth order means. So we have to choose what are the harmonics to be eliminated. So depending upon that, we will give some firing angles to the devices in the inverters. So in depending upon that, the corresponding harmonics alone will be reduced. So that is called the selective harmonic elimination. The harmonic has to be eliminated, should be selected for the according to that some equations will be formed, and from the output of the equations the angle, that is the firing angle or the triggering angle of the devices, will be altered. So depending upon that, the corresponding harmonics alone will be filtered. So that is called selective harmonic elimination, PWM. And we can go for multi-level inverters. So instead of single step inverters, so normally we will have this type of inverters in output waveform of the single phase. Will be having like this a square waveform. So this will be your V naught. So instead of this, we can say this is Vs and minus Vs. So this is plus Vs, and this will be minus Vs. So this is a two-step waveform, or it can be three-step with plus Vs, minus Vs, and zero. And instead of that, we can go for different higher levels. That is multi-level inverters. So the output waveform will be like this. So the number of levels or number of steps can be increased. So this is your multi-level inverters. The waveform will be like this. So this will be the positive half cycle, and the next one will be negative half cycle. So this can be a Vs and 2 Vs, 3 Vs, and the higher value will be 4 Vs. Likewise, we will have different steps. This is a multi-level inverter output waveform. So this also an advanced method for reducing the harmonic contents. We can compare both the waveforms. So this waveform, from this waveform, we have to extract the sine waveform. That is your fundamental, and that fundamental alone will be used for the giving the load, that is for supplying the load. So from this waveform we have to extract this type of fundamental. So the remaining will be harmonics that has to be filtered. And here also we have to take the sine waveform, that is your fundamental waveform. So this is your fundamental, that is sine waveform. So we are when we are comparing this, the multi-level inverter output waveform is more sinusoidal, that is it is approaching towards more sinusoidal when compared to this two-step or the square waveform. So by increasing the number of steps or number of levels, we can easily filter the harmonics, and by altering that output voltage waveform, that will approach more sinusoidal. So in this sense, the filtering can be easily done in case of multi-level inverter. So that are all the advanced techniques. In multi-level inverter also different types of PWMs are used for suppressing the harmonics. So since the harmonic is an important topic, that is your in the inverters, the harmonic, what is the level of the harmonic, why it should be avoided or why it should be filtered. So that is an hard topic in the industries. So in industries, they will invest a large amount for the filters for suppressing that harmonics. So or otherwise they will be penalized in your every month EB bill. So for any industrial applications or any industry is having HT supply means, so they have to maintain power factor within some range. So they will give the maximum value of power factor will be 1, and they have to maintain the power factor within 0.97. Likewise, they will give the limit. So if the power factor is reduced below the that value, for a prescribed value, means they will be penalized. And likewise, the harmonic content will also be predefined. The harmonic content should be less than 5%. If it is exceeded means, so they will be penalized. So the harmonics will be an important factor when you are going for the higher order applications. And so that is the basic methods are PWM, transformer connection, and stepped wave inverters. And this is one of the bipolar, that is harmonic harmonic direction by the PWM. That is by bipolar means it will have positive as well as negative negative voltages. So here we are having, this is your positive half cycle, that is up to positive half cycle, that will be the time period will be pi, and 2 pi will be your full cycle. The finish of full cycle will be up to 2 pi, and before that we will have number of positive and negative pulses. So if it is a single, that is it's bipolar, I have told bipolar in the sense it will have positive and negative waveforms. So if it is an unipolar means the waveform will be like this. So it will be only in positive in the positive half cycle, and only in negative in the negative half cycle. So this will be the pi, and in up to 2 pi there will be negative half cycle. So here it will be like this. So only the negative pulses will be there in the output voltage, right? So it will be the waveform for the unipolar PWM. So unipolar PWM in the sense, so the positive will have positive pulses alone, and this is a bipolar that will have positive and negative pulses in both positive and negative half cycles, right? So this is the firing angle, that is alpha 1 and alpha 2 are the firing angles. So we can segregate or we can bifurcate the cycle, that is a full cycle will be 2 pi, and half cycle will be pi, and the pi by 2 will be the 1/4 of the cycle, that is a quarter cycle, you can say half cycle, and this is the 1/4 of the quarter cycle. So here what will be the time period? It will be pi by 2. 0 to pi by 2 will be the time period for the 1/4, that is a quarter of the cycle. So for that we can define the firing angle for the devices. So alpha 1 and alpha 2. So by means of varying this firing angle alpha 1 and alpha 2 for a prescribed value of alpha 1 and alpha 2, or the for a optimized value of alpha 1 and alpha 2, the harmonics will be reduced. So we cannot choose randomly the alpha 1 and alpha 2. So we can choose by some mathematical methods the of alpha 1 and alpha 2 for suppressing the harmonics. So these are the that mathematical calculations. So here we can see the 10 commutations per cycle. So in previous diagram, so these are the numbers that is in denoting the commutations. So here it is turned off. So suppose we are having the four pulses, four switches means in the inverter we will have the four switches. So that four switches will be two will be turned on for each half cycle. That is positive and negative. So this will be 1, 2, 3, and 4. So here when positive half cycle is in the output voltage means the 1 and 2 will be conducting. Then it is in the negative half cycle means the 3 and 4 will be conducting. So the 1 and 2 has to be turned on at this instant. So this is the first computation. So computation means turn off process. So at the first computation, the first point, the 1 and 2 devices will be turned off, and the next 3 and 4 will be turned off in the second computation. So likewise, we can define for a full cycle, it will be 10 computations. So 10 times the switches has to be turned on and turned off. So that will be represented over here. That is 10 computations per cycle. And it is the Fourier series expansion. So for the calculating the optimized value of alpha 1 and alpha 2, that is here prescribed over here. For this, we have to go for the Fourier series analysis. So from that, we are solving some expressions to calculate the optimal value of alpha 1 and alpha 2. So here, it is a quarter wave symmetry. So quarter wave symmetry in the sense, so if we look the positive and negative, the waveforms are similar. That is, what are all the gap? That is the area of the waveforms in the positive will be will be similar to the negative half cycle waveform. So that is called half wave symmetry. And after that, we can have this pi by 2. That is pi by 2 means that is the quarter of the cycle. So in this also we can see, so this portion, what are all the nature of the waveform or what is the area of the waveform means. So the same will be replica in the another quarter of the cycle. So in the half cycle will can be divided into two quarters. So that in the two quarters also the area of the output voltage will be same. So depending upon that we can have it as quarter wave symmetry. So this is the quarter wave symmetrical waveform. For that, there will have in Fourier, according to Fourier analysis, there will be two coefficients. There is AN and BN. For this type of symmetrical waveform, the BN will be 0 and AN alone will be existing. And for this, we have to calculate the expression. That is a coefficient expression. That is 4 by pi. That is 4 by pi means. So we are taking it for pi by 4. So this is the pi by 4. So this is pi by 2. And after that, we will have the bifurcation within that quarter cycle, that is pi by 4. So we are taking it as pi by 4 as the time period, that is 1 by pi, 1 by pi by 4. So the maximum value of voltage is Vs. And first for 0 to alpha 1, and next one alpha 1 to alpha 2, and next one alpha 2 to pi by 2, right? So that will be, so up to pi by 2 we are choosing. So this is the time period we are taking for the analysis. So for that first one 0 to alpha 1, it will be having plus Vs, and alpha 1 2. So this is your alpha 2, that will be minus Vs, and after that that will have plus Vs from alpha 2 to pi by 2. So for that we have substituted, that is here it is plus Vs, and the next one it is minus Vs for alpha 1 to alpha 2, and again it will be alpha 2 to pi by 2, it will be plus Vs. So we can simplify this, that is 4 Vs by pi will be in outside, and 1 minus, that is 0 to alpha 1 sin n omega t. If sin n omega t is integrated means cos n omega t divided by n we will get. Likewise we have to simplify all the expressions, say cos n omega t by n. So we can substitute, and we can say substitute the limits. We can get the output expression like this. The an expression will be like this. So if the fifth harmonics and the third harmonic has to be eliminated, the n should be 3 for the elimination of third order harmonics, and n should be 5 for the elimination of fifth order harmonic, and that has to be equated to 0. So which harmonics has to be eliminated. And depending upon that, we have to frame the coefficient expression, that is A3 and A5, and that should be equated to 0. And we have to solve the expressions. So this term will be 0 and 3 will be 0. Finally, we will get 1 minus 2 cos 3 alpha 1 plus 2 cos 3 alpha 2 equal to 0 will be the expression for this. So this is your first expression, and this will be the simplification of this first expression, and the second equation simplification will be like this. So if we solve these two expressions by any mathematical methods, we will get the value of alpha 1 and alpha 2. That is, we are getting it as 23.62 and 33.304. So that will be the optimized value. So if we are switching it as, so if we make it as 23.62, so if we make it as 23.62, and if we make it as 33.304, we will have the output voltage with no third order and fifth order harmonics. So what will be the constraint means? So all the angles should be less than 90 degrees, since we are taking the limit as pi by 2. So up to this only we are analyzing. So all the values, the alpha 1 and alpha 2 should be less than 90 degrees, and alpha 1 should be less than alpha 2, and it should be less than 90 degrees. So that will be the constraint. So this is defined over here. The alpha 1 should be less than alpha 2, and it should be less than 90 degrees. So if we substitute this value, this optimized values, we will get no third order and fifth order harmonics. That corresponding harmonics will be 0. So here it is explained, that is third order and fifth order harmonics. That is there are lower order harmonics that will be eliminated, and the harmonic reduction inverter is derated by 16.07%. Derated means the efficiency of the inverter will be derated by 16.09 percentage. That is, the output voltage will be reduced by this percentage, and it is having 10 commutations per cycle. If you are increasing the commutations, means the switching losses will be high. So normal case, we will have two commutations. So the T1 and T2 will be conducting over here, and T3 and T4 will be conducting over here. So the T1, T2 has to be turned off at this instant alone, and T3 and T4 has to be turned off at this instant alone. So in full cycle, the commutations will be only two. So this is first one, and this is second one. So additional 8 commutations per half cycle when compared to the two-step inverter. So the depending upon the number of commutations, the switching losses will be high. So that is number of times we are turning on the device and turning off the device, means that will be the switching of operations of that device. So depending upon the switching operations, the switching losses will be increased. If a lesser number of switching, means the switching loss will be less. If the switching operations are increased, means the switching losses will be high. So this is the second method, that is by transformer connection. So already we have seen this connection, that is, we are giving the DC input and we are giving it to two inverters, and the output will be connected, each of the output of the inverter will be connected to two transformer primary, and the secondaries are connected in series. So this is the output waveform of the first inverter, V01. So that is a perfect square waveform, and this is having a magnitude of Vs, and in a minus, that is minus Vs, and V0 is also having the same magnitude, plus Vs and minus Vs. So what is the difference means? It is phase shifted by pi by 3. That is pi by 3, that is 180 degree divided by 3, that is 60 degree. It is phase shifted. So it is starting at the 0 degree. So it is starting at the 60 degrees. So likewise, the inverter has to be built. So both the waveforms will have same frequency and the same magnitude, but only difference is the phase difference. So here it is 0 degree, and here the phase difference is 60 degrees. Now we are adding the two output voltages, that is V0 will be equal to V01 plus V02, right? So in this case, here up to 60 degree, the V01 will be plus Vs and V02 will be minus Vs. So if you are adding, it means both will be cancelled. So up to 0 to 60 degree, the output voltage will be 0. And after this 60 degree to pi, this is the pi, that is 180 degree, the output voltage will be Vs plus, here also V02 is also Vs, so it will be 2 Vs. And likewise from pi to, that is 4 pi by 3, here it will be plus Vs, that is minus Vs, here it is plus Vs, so output voltage is 0. So likewise we will have the output waveform, that is, it is a quasi square waveform. So it is a perfect square waveform, and this is the quasi square waveform. So in this condition also, the harmonics will be reduced. So here it is explained, there is output of two inverters combined by means of transformer. The resultant voltage is V01 plus V02. So in the, what are the conditions means? So both the voltage waveform should be similar. That is in volt, in terms of voltage as well as frequency. Both should be similar but phase shifted from each other. So here the third and other triplet harmonics are eliminated. Triplet harmonics in the sense multiples of 3, that is 6, ninth order and the 12th order. These are the triplet harmonics. So that will be eliminated in this case of transformer connection. So here the D rating will be 13.4 percentage. So it is less when compared to the previous case, that is the PWM. So but what is the disadvantage means? So here the number of inverters and number of transformers are higher. So that will also reduces the efficiency of the system. So if the number of stages or number of components are increased in any of the system means, so that will reduces the efficiency, since the losses are high in each case, in each system. The number of devices are increased, means the losses will be increased in each of the device. So cumulatively the losses will be high, so that the efficiency of the overall system will be less. And this is the stepped wave inverters. So in previous case we have gone for the, both the inverters will have the same output voltage waveform but phase shifted to each other. But here the output voltage will have different magnitudes. So here also we are giving the input voltage. So this is your input DC, and it is out, the output will be AC, that is square waveform. And here we are using two transformers. So here we can see the turns ratio. This is 1:1 and it is 1:3. So the output voltage can be Vs. So it will be Vs, and here also it will be Vs means. So what will be its output across V01? So it will be stepped up by 3 times. So it will be 3 Vs. And here the V02 will be Vs, right? So by means of varying, that is a variable turns or the different turns transformer, we will have the harmonic reduction, that is called stepped wave type of inverters. So here we can see V01 will have 3 Vs maximum. So the output voltage can be 0 or 3 Vs for the V01. So it is a two-step inverter, and in V02 we will have 3 levels, that is plus Vs. So this is your plus Vs, and this is minus Vs, and this is 0. So likewise we have to make the inverters. So the first inverter will have only 2 levels, only positive, that is 0 or positive, and in V02 it will be plus Vs, minus Vs or 0. And the overall output, that is V0, will be V01 plus V02. So for each instant we can have the, what is the magnitude of the overall output voltage V0. So for this period, so for the first time period we can calculate. So here it is 0 and here it is Vs. So what will be its output? Vs. And the second waveform, so here second period, so it is 3 Vs and it is minus Vs. So 3 Vs minus Vs, 2 Vs. So it will be 2 Vs. Here it is Vs, and for the second period it will be 2 Vs, and for the third period, so it will be 3 Vs plus 0. So what will be its magnitude for this time period? It will be 3 Vs, and here it will be 3 Vs plus another Vs, that is it, the maximum magnitude will be 4 Vs, right? So likewise it is 3 Vs, 2 Vs and Vs. So this will be positive voltage alone. Likewise we will have the negative voltage. So in this case also the harmonics will be reduced. So here it is explained the step wave is generated by pulses of different widths and heights are superimposed, that is added, and the transformer will have different turns ratio. So first transformer will have 1:3, and second transformer is having 1:1 turns ratio. And here the first half cycle, the V naught is either positive, 0 or positive. In the second half cycle, the V naught one is either 0 or negative, that is two level modulation. So here in this negative half cycle, the voltage in the of the output of the first transformer will be like this. So this is for the positive half cycle and this is for negative half cycle. So this is also minus 3 Vs. So that is represented over here. That is second half cycle, the V naught one level is either 0 or negative. And in inverter 1, in first half cycle itself, we will have positive, negative or 0. And in negative also, negative half cycle, that is a second half cycle also, the output voltage will be positive, negative or 0. That is called 3-level modulation. The maximum output voltage will be 4 Vs. And the amplitudes of harmonics depends upon the width of the pulses D1, D2, D3 and D4 and the amplitude of V0. So by proper choice of this width, we can eliminate the third, fifth, seventh order harmonics. That is lower order harmonics can be eliminated. Right? So that are all the harmonic elimination techniques. And this is the current source inverters. So already I was told about the voltage source inverter. So voltage source inverter means the output voltage and the input voltage will be constant and the current will vary according to the load. So in voltage source inverters, if the output voltage is having V naught will be like this, a square waveform means the output current I naught will be of varying nature depending upon the load, the type of load we are connecting. So since if it is a inductive load or something that is RLC load means the current can be like this. It can be exponentially increasing and 0 and again it is exponentially increasing and again 0. So it will be like this. The waveform nature of the I naught will depends upon the type of load in case of voltage source inverters. But in current source inverters, it is reversed. The output current I naught will be constant irrespective of any type of load. So the output current will be perfect square waveform nature. That is for ideal case in case of CSI. That is current source inverters, but the output voltage will vary depends upon the type of load, right? So here the output waveform, voltage waveform can be like this. So here the output voltage is constant and it is in our current source inverter, the output current is a constant one. And the input current is constant but adjustable. That is, if it is 5 amps means throughout the cycle it will be 5 amps, but it can be increased to 7 amps depending upon the load requirement. Right? So that it mentioning it as adjustable and V naught is depending on the load. The waveform nature is depending on the load. Either it is R resistive load means it is same as the I naught, but for RL load and RLC loads, it is varies according to the nature of the load. And I naught is independent of the load. So it will be a perfect square waveform. And the frequency of output current F naught depends upon the rate of triggering of the SCRs. And I naught is adjusted by controlling the input current. So I naught is the value of the I naught. So that can be controlled by means of varying the input current magnitude. And it does not require feedback diodes. In previous VSA voltage source inverter, the feedback diodes are the important parameters for the RL load and RLC loads. But here the feedback diodes are not required. And here the computation circuit. Computation circuit means the turn-off circuit of the SCR will be simple. That is, it has having only one SCR. And in device in CSI, we have to withstand reverse voltages. So here the voltages, higher voltages has to be withstand by the devices that are connected in the inverters. The devices can be GTOs, power transformers, power transistors, power MOSFET, and IGBT cannot be used in CSIs since it cannot withstand the reverse voltage. So the device which will withstand the reverse voltage will be SCR. That is, it is having forward blocking state and a reverse blocking state. In both the forward and the reverse, it will block the voltages. So the SCR will be used in case of CSI. These are the devices which will not withstand the reverse voltage. So they will not have reverse voltage blocking capacity. And the applications are the speed control of AC motor, induction heating, lagging VR, reactive power compensation, and the starting of synchronous motors. And this is the circuit diagram of CSI, that is the current source inverter. And here also we will be having the four SCRs. So the same circuit, but it is somewhat modified. So when we omit this up to this point, and after this we can have the normal inverters. And before that we will have some voltage, input voltage device, input voltage source in series with an high inductance. So what is the necessity of this inductance means? So this plays a major role. So that will make the input current as a constant one. So it is a current source inverter. We have to converting it into current source by means of connecting in series inductance. So that is inductance of high value. So the purpose of the inductance is to maintain the input current as a constant source, so that we are converting this voltage source into current source. So the input is a stiff current source, and the output is also a perfect square wave form. That is output current. Output current is also a constant one. In here also, for positive half cycle of the output current, T1 and T2 will be conducting, and for negative half cycle also, the T3 and T4 will be conducting. So this is the waveforms for the ideal single phase current source inverters. So this is the input current, that is I input. Current input will be of constant magnitude I by means of connecting in inductance. And this is your output current I naught, and I naught will have the square waveforms. For positive half cycle of the output waveform, T1 and T2 will be conducting, and for negative half cycle of the output waveform, T3 and T4 SCRs will be conducting. So this is the full cycle for the I naught, that is output waveform. The magnitude will be plus I and minus I depending upon the value. Suppose it is 5 amps, the input current we are giving means the output current will have positive maximum of 5 amps and the negative maximum of minus 5 amps. So here it is the perfect square wave form since it is an current source inverters. And from this we can derive the V naught. So V naught can be derived by using the expression, that is I naught is equal to C into D V naught divided by dt. So, suppose we are having the capacitive type of load. So this C represents the capacitive type of load, means the I naught is equal to, we can have the expression, that is a normal expression, that is Vc is equal to 1 by C integral of I dt. So from this we can calculate the value of Vc, that is IC, that is equal to dVc by dt into C. So from this we have derived this expression. So here we have seen that I naught will be a constant parameter, and C is also the load, that is also constant, means the dV naught by dt, that is the slope of the waveform, will also be constant. So here we can see, so this is the slope. So this slope magnitude will be the dV naught divided by dt. So how we this is the slope. The rate of rise of V naught will be is equal to dV naught by dt, and this is the time period, that is the half cycle. For this, the dV naught by dt will be positive. So it is increasing from the negative maximum to positive maximum. So here the dV naught by dt will be positive, and after this, for the negative half cycle of the output current, we will have the dV naught by dt will be negative. So this, here it will be minus dV naught by dt. So the negative slope. So by this we can see that is the positive, for positive half cycle of the output current, the slope of the output voltage will be positive, and for the negative half cycle, the slope of the output voltage will be negative. So this output voltage V naught waveform. So from this we can plot the input voltage waveform. So what is the nature of the input? So output is an AC, the output current and the output voltage are AC, and input current and input voltage are DC. So if the voltage is having positive slope and negative slope means, so that will be considered as AC. And if the slope is only positive, so So that is V naught by dt is only positive, means that is considered as DC. So here it is increasing from 0 to, there is a negative maximum to positive maximum, and suddenly it drops to the negative value, and here also the negative, that is a slope is positive again. So it is a, look like a sawtooth waveform. So all the slopes will only be positive. So the negative slope will be 0. So at the the instantaneously the voltage is reduced to 0. So from this waveform we are drawing this input voltage. The waveform will be like this. So it is having only the positive slope, that is dV naught by dt will only be positive, and negative, that is minus dV naught by dt will be 0. So this is your input voltage waveform, and this is the input current waveform. So the frequency of the input voltage will be 2 times of your output frequency. So this is the frequency is the output frequency is f is equal to 1 by t, means the input frequency will be 2 times of your output voltage frequency. So this is your current source inverters. So this is explained over here, right? And the average value of Vin is positive, that is power flows from source to load. If the average value of Vin is negative, the power flows in the reverse side, that is load to source. Then in that case, a regeneration of the power will takes place. So there's a current source inverters will have load or force computation. Load computation in the sense, depending upon the load, the SCRs will be turned off automatically. That is for the capacitive type of load. The load itself turns off the SCRs, and force commutation means you will have some extra commutation circuit to turn off the devices. That is for lagging power factor loads. It will require some extra commutation circuit, that is called force commutation. For leading power factor load, that is a capacitive loads, you will have the capacitor itself turning off the devices, so that it is called as load commutation. The load present in the capacitance present in the load will turn off the devices, so that is called load commutation. Forced in the sense we have to forcefully, or we have to make some arrangements, extra arrangements, that is extra computation circuits to turn off the devices. So that will happen in lagging power factor loads. So after this we can finish. So in next class we can see the next topic, that is a single phase capacitor commutated CSI with resistive load. Thank you.